Hello and welcome to the second video in this series that I'm doing on how to do archival data research in Matlab. Before we get started in this video, I wanted to briefly point out the advantages of Matlab over a program like SAS, which is usually taught to PhD students to do archival research. SAS is a good program. Obviously, it's well used. Everyone knows it. Very popular. It can do a lot of powerful things. One of the advantages of Matlab over SAS is you get to see the data like no other. Matlab is the one software for data analysis where you really get to visualize the data. So, for example, you'll know if you've made a mistake in your coding a lot easier in Matlab than in SAS. And when I mean a mistake, I don't mean like an error where you try to run your line of code and you get an error message. Obviously, if you do that in SAS, you're going to get an error message if you type the wrong syntax. No, I'm talking about where you run your lines of code and they run fine, but you haven't really done what you intended to do with those lines of code. In other words, you have a mistake in your code. You say you're doing X, but really you're doing Y or something like that. Where in Matlab, it's harder to do that because you visualize the data. You get so acquainted with the data in the rows and the columns that it's harder to make mistakes like that where you mess up. Now in Matlab, it takes longer to code and to produce a certain output than it does in SAS. SAS is really powerful. The functions are really powerful, but they do so many things at once that you don't even get to see what's actually being done. You can't visualize the data as well in SAS, and therefore you don't know if you've made a mistake. And you don't come away with, intuitively understanding exactly what you did, as well as if you use Matlab to do your coding project. So that's the main advantage. I remember when I was a PhD student, I used to have this argument with one of my professors, and they had assigned us a project. We had to replicate a paper. We had to replicate a couple of tables in a paper, the main tables, and he wanted us to use SAS. And I had been using Matlab for several years before that, and I was like, well, I'm just going to do it in Matlab. And he's really wanting me to use SAS, and I'm like, well, I don't want to learn a new program if I already know how to do it in the current program. Why learn two programs if I can already do it in one of them? So he said, all right, if you can replicate the tables, I don't think you can, but if you can replicate them in Matlab, you can use Matlab. So I did the replication. I replicated the tables fine in Matlab. And ever since then, I've been an advocate for Matlab over SAS. I know I'm in the vast minority in terms of archival data researchers in accounting and finance. The majority of them use SAS, but I love Matlab. There's nothing you can't do in Matlab, where in SAS, there are things you can't do. It's not particularly good at doing some types of econometric things, although it's gotten better. So that's my blurb, my pitch for Matlab. In Matlab, what you're wanting to do with any data project is you're wanting to visualize the data. Visualize what you want the output of each step in your code to be. And you make that visualization come to pass. Make it a reality. And when I mean visualize, I mean what matrix do you want to show up in the end with the columns and the rows? And so let's get into today's video. So in today's topic, I'm going to be showing you how to compute financial ratios using Compustat data. So we're going to be computing financial accounting ratios using Compustat data. Now the data is going to, well, before I get started, I've created this folder and I'm going to share it with whoever asks me. If I receive feedback on this video that people want me to share this folder with them, then I will. And inside this folder we'll have our data. So this will be all the data sets that I'm going to use throughout this video series. This is the data set I'm going to use today. We'll have a literature folder where if we're replicating a paper or something, I'll put that paper in here. Anything to which we are referencing in terms of papers or things like that, literature, then I'll put those things in here. And then programs, this will have our code that we're writing. And for each video, I'll name the script file appropriately, so you'll know to what that script file of code references. Like this script file, I'll probably call something like computing financial ratios or something. I'll name it that. And that way, if you have Matlab, you can, and I share this folder with you, you can download the data, you can download the script file that I used, and then you can see if you can do the same thing that I do, typing your own code in Matlab, and just see if you get the same results that I do. And then you'll always have my answer key, so to speak, to fall back upon if you get stuck. So let me know in the comments or send me an email if you want me to share that folder with you. All right, so let's get started. So Compustat data. The data, I've already downloaded the data and I put it in here, and I've made it a CSV file, and I've called it Compustat quarterly 2014 through 2023. So what I've done is I've just grabbed the 10 most recent years of quarterly Compustat data from Words. What's Words, you might ask? Well, if you're an accounting or finance PhD student, you'll know what I'm talking about. But in case you're not, I will clue you in. So Words, WRDS, Wharton Research Data Services, it's a main data provider for academics who do research in accounting and finance, who do business research. They're located at the University of Pennsylvania, and they have a bunch of data. They're just a data provider, and they sell their data. So usually to get access to Words data, you have to be a faculty member or a PhD student at a university that subscribes to the data. And the subscriptions are expensive. So they're prohibitively expensive, so an individual can't really afford the data. We're talking about tens of thousands of dollars per year to be able to get access to some of this data. So if we log in here, so here are all the subscriptions that you can access, that are available. And when you click on a particular thing like Compustat, typically, if you look here, in each of these categories of data, we have a number here. This is how many individual data sets are inside this category of data. So Compustat and CRISP are the two most frequently used little databases that are inside of Words. Compustat has 179 different data sets, and CRISP has 341 different data sets. These are the two most commonly used databases by accounting and finance researchers. Compustat contains all of the accounting fundamental data, information that'd be on a company's financial statements, their balance sheet, their income statement, statement of cash flows. These types of data will be in Compustat. And then CRISP has all the information about stock prices for a company. Daily stock prices, monthly stock prices, daily stock returns, monthly stock returns. So if we go to Compustat here, and if it's grayed out, if a given database is grayed out, that just means you don't have access to that particular database. So Compustat North America is where the main data is in Compustat. And I pulled the data that we're going to be using in this video from this fundamentals quarterly data set. It has quarterly accounting data. And you'll see which variables I pulled whenever we look at the data. So I've already downloaded the data. I'm not going to teach you how to download data from Words. I'm assuming you know how to do that already. You can either come in here and do it this way, or you can do it, if you have SAS, you can do it behind the scenes. And in Matlab, I think you can do it behind the scenes as well. You have to, there's an API that you can get to connect the back way, so to speak, to Words, and then you type in your username and password, and then you can pull the data in directly from Matlab. You don't have to go to their website like I'm doing and downloading it. But I just do it this way because it's easier for me to do it this way. But if you want me to make a video on how to do it the back way, I can do that. All right. So we want to get the data, and I'm going to go ahead and pull that data into our file here. The first thing I'm going to do in our script file, notice I've made a new script file here. Let me close this. We made a new script file, and there it is. And we're going to actually end up saving this script file when we're done and putting it in that programs folder that I showed you earlier. So usually with any script file, I give myself a message at the beginning of the script file so that I know what this code that I'm about to type, what it does, what this script file does when I come back to the script file, 6 months from now, 2 years from now, when I haven't used the file in a long time and I forgot what all this code does. So you make yourself a message, or if you want to share script files with a friend or another researcher, a co-author, and they want to know what your program does, then you make them. Definitely don't just type lines of code. Definitely put your descriptions and your comments to yourself in your script file. It makes the code easier to understand later on when you come back to it. So this code computes various financial accounting ratios using the past 10 years of Compustat data. Now I just picked, for my data set, I just picked the last 10 years of quarterly Compustat. Certain variables, you'll see which variables, but I could have picked the entire Compustat, all the way back to 1950, which is when Compustat starts reporting data, but I didn't get all that data. I just grabbed 10 years. So here's our script file. Now I'm going to go ahead and Control S. We're going to save our script file. We're going to save it here in our programs folder. I'm going to call it Computing Financial Ratios. When you name a script file, you can't have any spaces in the name. You have to have all characters, including an underscore as an example of a character you can have in it, like this. You can name things like that if you want to, but I usually just delineate my name with I just capitalize the first letter of the word. So computing financial ratios is what this script was going to do. First line of code I type in any script file is I clear vars, like I taught you in the last video, in my introductory video. And this clears the workspace of any variables that are currently there, if there are any over here, but there aren't any, of course, right now. And then I do type CLC, and of course that clears the command window down here like I taught you in the last video. All right, now I want to bring in the data. Now the data resides in this folder. The data resides in this folder right here, which is in my Dropbox. It resides right here in this folder. There it is. So when you bring in your data, you need to point Matlab up here, right up here in this row. This is the path where you point Matlab to where the data is. So I already have it directed to the right place, but you click this and you find on your computer where the data is. For me, it's in Dropbox. It's right, my data resides in this folder right here. So you just select that folder, and that points Matlab to the right folder. And then you can pull any data sets that are in that folder into Matlab with the following command. So I'm going to call this data, I'm just going to call it initial data. And I'm going to use the read table function. So I'm going to pull this initial data, and you see how by default it gives all the names of the files that are in this folder on your computer already. Instead of me having to name it, I can just click this here. So you name the file, you tell Matlab which file you want to pull into Matlab. It's that file. And then we want to preserve variable names. Set that to true. So this is how you pull in data to Matlab. You always have this first argument, which is the name of the file. Make sure this file is in this folder where you've pointed Matlab. If there are no files in this folder that have this name, then when you run this line of code, it's going to give an error. And then the second argument is the preserve variable names argument, and you set that equal to true. By default, preserve variable names is set equal to false. In other words, if you don't put any of these arguments here and you just run this, then the names of the variables in this CSV file won't be preserved whenever you bring this file into Matlab into a table. In the table, the variable names would just be variable 1, variable 2, variable 3. It'll give them those generic variable names. But we don't want... Here, I'll show you what it does. If we bring these in like this, run this line of code, highlight it, and push F9 on the keyboard. See, it'll bring in the data, but the variable names won't be preserved. Actually, it did preserve the variable names. I'm not sure exactly why. I'm used to having... I thought variable names are not preserved by default. I thought these variables would just be named var1, var2, var3, var4, var5, but it actually kept the variable names as they were in the file. So that's something I learned. I'm used to having to type this particular command, specify the second and third arguments of this read table function to make sure that the variable names are there. But it looked like it did it anyway. I'm going to keep it like that, though, just in case. So this bring in data. Make sure this data set right here with this name, is in the path folder, is in this folder. This is the path folder. So set the path to the right folder, then you can bring in data from that folder into Matlab with this command. Now, if we look at the data, we can see we have 21 variables. We have GV key, and I'm going to assume that you all kind of know what some of these variables are, that you're used to using Compustat and or CRISP. You're a PhD student or you're a faculty member, and you already have an idea. So the GV key is just a company, it's a numeric identifier for the company, what company it is. Then we have the day, or the data date. Then we have the fiscal year, we have the fiscal quarter, and we have the fiscal year end month. So for this particular company, this row is reporting observations on these variables right here for fiscal quarter 3, fiscal year 2013, and that fiscal quarter 3 of fiscal year 2013 ended on this date for this company here. Now, what are these other variables here? Oh, notice that this particular company does not have a 12/31 fiscal year end. Its fiscal year ends in May, the last day of May. And that's why at fiscal quarter 3 for this company, 2013, is actually ends on February 28th of 2014. You know, usually fiscal quarter 3 for a company ends when? It ends on September 30th, right? That's when a fiscal quarter usually ends. Fiscal quarter 3 ends for a 12/31 company, for a company whose fiscal year ends in December. But if the company's fiscal year, if their fiscal year end doesn't align with the calendar year end, like this company, then then the dates could be different. So for this company, their fiscal year begins on June 1st. So fiscal year 2013 began on June 1st and ends on May 31st of 2014. So the end of the third quarter, fiscal quarter for this company whose fiscal year is 2013, fiscal year end month is May, is this date right here. I'm assuming that you guys understand the idea with fiscal years and calendar years and fiscal year ends versus calendar year ends, and you know that. Now, here are all the variables right here. All of these are the main variables we want to look at. So we're going to be computing several financial statement ratios. So I've got all the data I need to compute the ratios that I want to compute. So this is the current assets at the end of the quarter. This is the total assets value at the end of the quarter. This is cash at the end of the quarter. This is cost of goods sold at the end of the quarter. This is the number of common shares of stock outstanding in the shareholders' hands at the end of the quarter. These are the dividends. These are the preferred dividends, the dollar value of the preferred dividends that are declared as of the end of the quarter. This is the dollar value of the short-term investments at the end of the quarter. This is the current liabilities at the end of the quarter, long-term liabilities at the end of the quarter. No, this is total liabilities at the end of the quarter, just like this is total assets at the end of the quarter. So current liabilities, current assets, total liabilities. This is net income at the end of the quarter, or for the quarter. This is preferred stock, the balance in preferred stock at the end of the quarter. This is the balance in receivables at the end of the quarter, all receivables. This is the balance in, this is the net sales revenue for the quarter. And this is the total stockholders' equity at the end of the quarter. And this is the company's standard industrial classification code. It's which SIC industry they're in. So the SIC industries have numerical codes, and you can either look at the 2-digit SIC industry, which would be the first 2 digits of this number, or you can look at the 4-digit SIC industry. And by default in Compustat, SIC is the 4-digit at the 4-digit level. Now, what actual industry does this reference? Well, we'd have to go find that elsewhere online. We'd have to have another file where we match it up. But in this video, I won't do that. Like, for example, this could be manufacturing or something. I'm just making stuff up. But we don't know for sure unless we go and find this information. I think the S&P website, so Standard & Poor's is the one that does the standard industrial classification. And we can go and, like, for example, let's see, S&P, or just type in SIC 4-digit. None of those look. Right here, sec.gov has the list of the 4-digit SIC codes and their corresponding industries. So, for example, that in that one 5080, what is 5080? That is wholesale machinery, equipment, and supplies, for example. But anyway, and you can download this as an Excel file or a CSV file and pull that into Matlab, and then we could join that with this and get the name that corresponds to each of these 4-digit SIC codes. We could do that, but we won't do that in this video. At least I don't think we will, unless we have time at the end. And this variable right here, which I haven't said what it was yet, this is the adjustment factor to adjust the, this is the quarterly adjustment factor to adjust share numbers and or price numbers. So the only thing we have that could be adjusted would be these common shares outstanding. So you multiply the shares outstanding by the adjustment factor, and that adjusts this number for any stock splits or dividends that may have occurred. Any stock splits or stock dividends that may have occurred during the quarter. So to get the actual common shares outstanding at the end of the quarter, it's this times the adjustment factor. Now, for the most part, the adjustment factor is 1 because the company did not split their stock or didn't give a dividend on their stock in that particular quarter of that particular fiscal year. But any instance where the adjustment factor is not 1, like here it's 2. Trying to give a good example here. Like here, there's the number of shares outstanding as of the end of fiscal quarter 3 2020 for this company, but they must have had a split previously, and this is the adjustment factor. This is the cumulative adjustment factor. I should have said that, the cumulative adjustment factor. So you can always just multiply these two numbers together to get the actual shares outstanding. So they must have done a reverse stock split in the past. If they did a forward stock split, then the cumulative adjustment factor would be greater than 1. And if they did a reverse stock split, then the cumulative adjustment factor would be less than 1. All these numbers here are in millions. These are millions of dollars. This is millions of shares. These are all millions of dollars. But this adjustment factor actually obviously is just a number. It's not in millions or anything. And these obviously aren't in. So the units of all these variables are millions of dollars. This, in the case of variable 11 here, it's millions of shares. So all of that should be pretty explanatory. So this is what self-explanatory. So this is what the data looks like. The first thing I can see that we might want to do, I'm just going to show you how to do this, is take this date variable. If we look at the variables, they're all double arrays. All the variables have a double data type, which is just a normal numeric data type. They're all double. Except for this one. This one has a date time data type. So usually with these dates can be sometimes tricky in certain programs, but in MATLAB we just want to convert this data date variable to a double data type. But if we do that, we have to get rid of these slashes. So I want to redefine these years. I want it to be in a different format. I want it to just be 4 digits for the year, so Y, then 2 digits for the month, MM, and then 2 digits for the day, DD. So this will turn into 20140228. It'll turn into that number with no forward slashes. And I want to just make this variable a numeric array, not a date time variable. You often will want to do that. So how do I do that? Well, what I'm going to do is, let me just show you how piece by piece the code. So if I do this, there's a function, YYMMDD. That's a function in MATLAB. And if I take a particular variable, a particular date time variable, it'll convert that variable to a numeric array and put it in this format. So the date time variable in question is column 2 of initial data. So if I take initial data, all rows column 2, you have to do it this syntax because initial data is a tabular, it's a table array. See, it's a table, it's not a double array. If it was a double array, you could just do like this. But then that includes the column headers as well. So if you just want the part of the table that's not a variable name, in other words, just a double part of the table, you got to do this syntax. So what does this do to column 2? It just outputs, what if, let's just call this, set day equal to this. So that's just going to create this, that just gives us a column vector day, which is column 2 of initial data, but now it's a double, you see, and we've changed the way the dates appear. Instead of 02//28/2014, we have the date in this way, in this sort of format. So this is a cool function. But now we want to recreate this table. So we want initial data to equal what it was before, all rows column 1. That's column 1. And then we want this right here to be column 2, but this is a double array, right? This is a double array. We want it to be back to a table array if we're making a table. So we have to use the function array to table to put that back into a tabular format so that we can put that as the second column of initial data. And then the columns 3 through the rest of the columns. An array to table has, you also have to specify variable name. How do you want to name this variable? So this right here is just a column vector, right, of the dates. And it's a double array. But now we're converting that double array back to a table using array to table function. And then what name do we want to give that column? It was given the name up here of data date, but I want to give it just the name of day. So this right here, this part of the code, it it takes a second column of initial data and makes it a double array in the YYYMMDD format, this part. But then we take that and put that back, convert it back to a table with this function, and we give the name, there's only one variable, we give the name day. And that'll be in column 2 of our initial data matrix. So we're redefining initial data now. It's initial data the way it was before, column 1. And then column 2 of this new initial data will be the old column 2 of this, but where we've redefined the day in a different format. And then columns 3 till the end, 3 through 21 of this will be the final columns of this. So initial data, all rows, columns 3 through end. End means go to the last column or last row. So I know that's a lot of code, but what we've done is we've changed the format of day variable and we've made the data type double, but then we put it back into a table. So let's run that. So let's look at initial data before we run that line. It looks like this. And let's look at initial data after we run that line of code. Oh, I forgot to put a semicolon after the code. And if you forget to put a semicolon, it starts putting the results of your code down here in the command window instead of only over here in the workspace. And we only want it to be in the workspace. So you have to put a semicolon after each. We can run this again. Incorrect number or types of inputs or outputs for function YYYMMDD. What did I do wrong? Oh. So let's start over. Let's bring the data in. So clear vars, CLC, and bring the data in. And then let's run this. There we go. Now look at the second column of initial data. We changed the name of the variable to day, and it's not in that format anymore. It's in this format, and it's a double array. If you see here, see it's double data type, not a date time data type anymore. Now all the variables are a double data type. All right. Now what we want to do is we want to convert all this data to just a double array. We don't want it to be stored in a table array anymore. I mean, we'll leave initial data like it is, but we're going to create a new array. We're just going to call it A. And it's going to be it'll only be the part of initial data, not including the column names. It's just going to be this part here, you know, just the actual data, not the column names. And it's just going to be a double array because it's faster to work with double arrays than with tables. Working with tables in Matlab, it takes Matlab longer to run the code if it's in a table format than in a double array format. So A is just going to be a double array. We're going to take initial data, all rows column 1, that'll be column 1 of A. And then columns 2 through the end will be initial data, columns 3, all rows columns 3 through the end. In other words, we don't want column 2 of initial data in our matrix A. We don't need it. We don't need the day. As you'll see later in the code, we don't need the day. Convert to double array for faster computations. Working with table arrays is slower in Matlab. So that's why I'm doing this. And we don't need day variable, which is why I did not. Look, I left out column 2 of initial data. I defined A as column 1 plus all the other columns except for column 2. And remember, column 2 was this column. We don't need the last day of the fiscal quarter for that fiscal year to compute financial ratios. We do need to know what fiscal year it is, what fiscal quarter, but we don't need the day. We don't really need to know the fiscal year end month either, but I'm going to keep that variable. So this will be A. We'll run this. Oh, you see what happened here? Let me stop this. To stop the code, just push this right here, or you can come down here and hold down Control C. The reason it's doing this is because I did not put a semicolon at the end of the line of code, like I keep telling everyone to do, but I keep forgetting it myself. So let's clear the command window and then let's run it again. All right, so A is just initial data, but we've left out column 2. You can see it has one less column than the initial data. But notice it's not a table array anymore, it's a double array. See, it's not a table, it's a double. The downside is we lost our column headers. So we don't know which column is which unless we go back to initial data and we know what the columns are. And that's the hardest part in Matlab, is dealing with the data where you don't have the column names. So you have to remember what column is which. So the way I deal with that is I bring in the data into a table to begin with, in which we do have the column names, and then I can always reference back to that table if I forget which column names. The only thing here is A and initial data aren't exactly the same. A doesn't have the date variable. In other words, column 2 of A is not the date variable, it's the fiscal year variable. So we just have to remember. I think you can just subtract 1, right? So initial data, if we're variable 10, cost of goods sold, quarterly cost of goods sold, the cost of goods sold for the quarter, that will be variable 9 of A. This $305 here will be $305 million will be it'll be in variable 9, right? We just subtract 1 because there's one less variable in A than there is in initial data. All right, something really important next is you want to sort the rows of A by firm, so by column 1, by fiscal year, by column 2, and by fiscal quarter, by column 3. In that order. You sort by firm, then fiscal year, then fiscal quarter. Now, the data already appears to be sorted in that way, and it is whenever you download it from Compustat. By default, it's sorted in that way. But just in case it's not sorted in that way, I always, as a rule of thumb, I always just sort the data right away in a way that I know it needs to be sorted. Otherwise, what we do later in our code will not work. It'll be messed up. So the sort rows function has 2 arguments. The thing you want to sort the row, the double array of whose rows you want to sort. The second argument is by what column do you want to sort the rows of this matrix? If we just do that, it'll sort the rows of A by column 1. Well, we want it to do it by column 1, then by column 2, then by column 3. So we put in brackets here 1, 2, 3. And that will sort the rows of A first by column 1, then by column 2, then by column 3. And so we've just set A equal to the version of A in which the rows are already sorted. I mean, you can keep A as it is and just let B equal this, but then you got so many different variables you're having to think about. So this basically just changes A to be sorted. And the way it sorts is it does it in ascending order by default. If you want to sort the rows of A by column 1, then by column 2, then by column 3 in descending order, then you have to specify a third argument of this function, sort rows. And as I said in the last video, if you're ever having trouble understanding what a given function in Matlab does, just look up that function online and go read the documentation. Here's the sort rows function. You can see we're using this particular version of it. It sorts the rows of A in the order specified by direction. Direction can be ascend, that's the default direction. So if you don't put anything, then it does it in ascending order. Or it could be in descend. It could be descend, and we did it in descending order. And then it gives examples. It'll give examples. So E sorts the rows of A by column 4 in descending order, for example. And you can see that if A looks like this, then E, we're going by column 4 in descending order. So the 95 should be at the top, then the 93 underneath that, and the 3 should be all the way at the bottom. 95, 93, 84, 79, 65, 3, as you see that right there, column 4. So you get an idea of how these functions work just by using the extensive MATLAB documentation. Now, at first, when you're learning MATLAB, it's cumbersome. There's a big learning curve to figure out what all these functions do. But that's what these videos are supposed to hopefully get you up to speed and make that learning curve not so steep. But we don't want to do in descending order. We want to do in ascending order. And so but that's the default order, and we'll just do the ascending order. But I mean, I went ahead and ran that line of code. Of course, A was already sorted in that way in the first place, so that really didn't do anything to A, but I always run that as a rule of thumb, just in case. Okay, in case A is not sorted. All right. Now what I'm going to do is I'm going to take my A matrix, and I'm going to pull out, I'm going to make a separate little double array for each firm. So this first firm, 1004, which ends on row 40, here's its data right here on all the variables. This little double array right here, this little matrix, if you will, it has what? 40 rows and 20 columns. This is just the data for firm 1004. I want that to be in its own little matrix. And then the data for firm 1019, I want that to be in its own little matrix. So I get the data for each firm in its own little matrix. And then I can write code on each of those little sub-matrices, if you will, to compute the financial ratios. And so to do this, I first need to get a vector of the unique firms. So I'm going to let U equal that vector. So let U equal, and I'm going to use the unique function. So the unique, what are the unique observations? All rows of column 1 of A, because it's in column 1 where the GV key is, right? This is the GV key in column 1, and this is the unique the GV key uniquely identifies a firm. So I want to find all of the firms, the unique firms. So I run this. And so you see that U has, there's 19,363 unique firms, and here are those firms: 1004, 1019, 1045, 1050, and so forth, as covered by this 10-year time period of data from Compustat. That's a lot of firms that are represented in this 10 years of data from January of 2014, January 1st, 2014 through December 31st, 2023. All right. And then what I'm going to do is I'm going to write a for loop. Again, I want each firm to have its own little matrix. I want each of these firms to have its own little matrix with the data. With just the data for that matrix, just the data for that firm in its own little matrix. Like for the first firm here, I want all this data to be in its own little matrix. And then for the next firm, 1019, I want its data to be in its own little matrix. So I guess I'll have 19,363 little matrices. Each matrix will be the data for each of these unique firms. So what that entails in MATLAB is making a cell array. A cell array is a matrix of matrices. So each element of a cell array is itself a matrix with a certain number of rows and a certain number of columns. So I want to do a cell array. I'm going to write a for loop. So for, I'm going to increment with I, so let I equal 1, increment by 1, and go all the way to however many unique firms we have, which is how big U is in the row direction, 19,363. So instead of typing 19,363 here, that's a very specific code. Then if I bring in other data and U doesn't happen to be 19,363, it happens to be some other number of firms in terms of the size of U, then I'll have to redo this part of the code. So you always want to make your code as general as possible. So I'm just going to say, I'm going to use the size function. In other words, how do I get this number right here, this number of rows of U? You use the size function. So size of U in the rows direction. This is the syntax. This will spit out 19,363. That's how big U is in the rows direction. If you want how big is U in the columns direction, you do that, and that would spit out the 1 there. So I use this function a lot. So I will start at 1, we'll increment by 1, and we'll go all the way up to whatever this is, which is 19,363. And so our little matrix, our little cell array, we're going to call it just firms. Row 1, column I of this cell array. Remember, a cell array is itself a big matrix with a bunch of rows and columns. Each cell in that cell array is its own matrix or a double array. So I'm only going to use the first row of this cell array. I don't need the other rows, just the first row. Column I will be equal to the portion of A, so row I will be equal to whatever U of I, wherever you can find U of I in A. So if we set I equal to 1, then the first submatrix right here will be wherever you found the first element of U in A. It'll be all that portion of A where you find this in the first column of A. Right? So remember, I taught you all logical indexing last time. So U11, that's the first row, first column of U, which is that 1004. So this evaluates to 1004. So we'll logical index. I'm going to show you what each little piece of the code does that I'm about to type instead of typing it all at once. What does this spit out? This spits out a logical vector, which will be, look, just like this. And there'll be a 1 if this condition holds. So if U11 is on that first row of A, column 1, remember U11 is 1004. So if you find 1004 on that first row of column 1 of A, which you do, then there'll be a 1 here. And if you don't find it, then there'll be a 0. So you'll see all these other places it's 0. Because you're only going to find 1004 in A for the first 40 rows, and then after that it moves on to the next firm. And so now all we have to do is take A of these rows right here, all columns, and that right there will be a little matrix. It'll just be the portion of the matrix of A with just the 1004 data. See, I'll run this and you'll see. See, it's just that 40 by 20 sub portion of A with just the 1004. Because this is a logical vector right here, as we saw already. It has a 1 if U11 is on that particular row of A and it has a 0 otherwise. And then when you put this, these are the rows of A that we want, and it'll only grab those rows where that logical vector is equal to 1. That's how it works. And it won't grab those rows of A where the logical vector is not equal to 1. So that's what we want in general. So we want the ith column of the firm's cell array, the ith little submatrix, or the ith little matrix in the first row of the cell array of firms. We want that to be wherever you find ui of 1, wherever you can find that in the first column of A, and then and just as we did, this is just the general form. This is the general form of this. So this holds for all I, right? When I equals 1, you get this down here. When I equals 2, you get something else. So these are the rows in the first column of A where ui of 1 was found. If I equals 1, that's where 1004 was found. If I equals 2, that's where 10019 was found, and so forth. So each firm gets its own little submatrix. So let's run this. See, it says busy down here. When it doesn't say busy, that means it's done. This step takes a second because we're trying to find, A is pretty big, and we're trying to find where all these 19,363 firms are. So here's our firm's cell array. You can see how it says cell. It has one row and it has this many columns because of the way we defined it here. And since it's so big, usually you can open this up and you can click and you can look at each of the little submatrices in this cell array. But since there's so many submatrices, 19,363 to be exact, it won't let you even see them. See, it just says here like this. It won't let you open it up and see, like here, let you see answer, or let you see U, or let you see but it's just because it's so big. So one way we can see, if we want to see the first one, we can just type firms 1, semicolon, and look at the answer. And that's right, that grabbed out the portion of A corresponding to that first firm, 1004. What about firms 1, 2? That should grab the portion of A that corresponds to that second firm, which was 1019. So if we look at answer, and there's the portion of A that corresponds to that second firm. Now that particular firm had a lot of missing observations on the variables, as denoted by Nan in Matlab. And let's just check. What if we want the portion of A that corresponds to this firm, the 22nd firm? Well, then we should just be able to do that. And that should give us 1209, the portion that corresponds to 1209. If we look at that, there it is, 1209. So we did our code right. So each firm has its own little submatrix. So this line of code created cell array of firms. All right, now I want to compute the ratios. What I want to do is set up a separate matrix. I want to do a separate cell array for the ratios. I don't want to put, so like for firm, let's take this firm right here, which was firm 22 that I pulled out, firm 1209. Here are all of its variables. It's accounting fundamentals, which we'd have to go back here to see current assets at the end of the quarter, total assets at the end of the quarter, total cash at the end of the quarter, and so forth. Here are those things for this firm. I don't want to put the ratios over here in the same firm's matrix. I want to put them in a separate matrix where it's just the ratios. That way we won't confuse the ratios with the actual numbers that we use to derive those ratios. So what I'm going to do is I'm going to say let I go from 1 to 1 up to the size of U in the rows direction. And I'm going to let ratios, the ith little submatrix of the ratios vector, equal just a portion of the corresponding firms one. So if we want firms 1, 1, what does that look like? It looks like this. And I want my ratios little submatrix to be the first column of firms, which is the firm, the GV key, the last column of firms, which is the SIC code, and then fiscal year, fiscal quarter, fiscal year end month. So all rows of firms, and then which columns? Column 1 first, then the last column, and then columns 2 through 4. You always have to put an end after a 4, otherwise every 4 has to have a matching end or you'll have an error in Matlab. So we just did a little for loop. So this creates a new cell array for the ratios, keeping only certain variables. I moved SIC variable to the second column, right? I put the last column was a SIC variable, and I'm end the last column. So you don't type last, you type end in Matlab. That means the last column or the last row. So I want the ratios, each element of the ratios cell array to be that same, and each element is a matrix, by the way, to be that same element corresponding to the firm's cell array, but not all of it. All rows, but only columns 1. The last column will be column 2 of this new ratios array, and then columns 2 through 4. In other words, if we run this here, the first ratios, and there's so many of them, if I click on this, it won't let me see them, so I have to just run, I just run this piece. There's the first ratios. It's all I did was grab the first column of the first firms, the last column, and then the other columns 2 through 4. See, if we do firms 1, 1, I grab this column, I grab this column, put that as column 2, and then I got these columns. That's what we saw in the ratios matrix. For the first element in the ratios array, cell array. All right, and then what I'm going to do is I'm going to fill in the each ratio. I'm going to let column 6 be the current ratio. Column 7 will be, I forgot my paper here, will be the quick ratio, and so forth, and you'll see which ratios I'm going to do. So I'm going to do a big for loop. The first thing I'm going to do is I'm going to first compute all the ratios which don't involve multiple quarters. And what do I mean by a ratio that involves multiple quarters? Like a ratio that involves the average of something in the denominator. A ratio is obviously a numerator divided by a denominator. Some ratios are you have to have at least 2 quarters of data to compute that ratio, right? In other ratios, you don't need to have at least 2 quarters. You just need that quarter's data. In any ratio in which you need to compute the average, you know, at the end of this quarter, the end of last quarter, then you need at least 2 quarters of data. So I don't want to do those ratios first. Those are the harder ones. We'll do those next. But for now, I'm gonna do the ratios that don't involve, they only involve 1/4 of data. So things like the current ratio, the quick ratio, the debt to assets ratio, the debt to equity ratio, the gross profit ratio, and so forth. So I'm going to do a for loop. I will start at 1, increment by 1, and go up all the way to how many of our firms we have, which is the size of U in the rows direction. And our little ratios, cell array, ith column. When we get inside that matrix, all rows, column 6, this column, all rows, column 6, it's going to be the current ratio. So the current ratio, if we go look at firms 1-1, the current ratio is current assets at the end of the quarter, the dollar value of current assets divided by the dollar value of current liabilities. So which column was current assets? Again, we have to go back to initial data. Current assets, which was in column 7 in our initial data. But remember, when we went to A here, we got rid of one of the columns. We got rid of the day column. So it should be column 6 in our little firms matrix. And it's column 6 here. So that's current assets. And then we want to divide that by current liabilities, which in our initial data was column 14, which means in here, this is our column 14, which means over in here it should be column 13. And that is. So it's 6 divided by 13. So firms, all rows, column 6. Now you want to divide by column 13. You know, I want to take all these rows divided by all these rows, element by element. This divided by this will be the current ratio for this company in the third fiscal quarter of fiscal year 2013. And then this divided by this will be the current ratio in fiscal quarter 4 of fiscal year 2013 for this firm. So when you want to do an element-wise division like this, you can't just put divide. That'll be an error. You have to do a dot and divide. That's element-wise division like this. All rows, column 13. This computes the current ratio. Next, in column 7, I want to be the quick ratio, or the acid test ratio, if you will. If you guys can remember back to basic accounting, basic financial accounting. So the quick ratio, we have 3 things in the numerator. We have cash added to short-term investments or marketable securities, if you will, and then added to receivables, and all of that divided by the current liabilities. So I want to put all of that. So cash, I think, if we go back here, cash is in column 9, so that should be in column 8 over here, and so forth. You just have to subtract 1. So we want firms, all rows, column 8. Then with adding and subtracting, you don't have to put the dot. You don't have to do this. If you want to do element-wise adding and subtracting of vectors, then you can just put the addition sign. So we want to add column 8, that's cash, to column, what was the short-term investments? Or the marketable securities, if you will. That was column 13 in our initial data, but it's column 12 in our... So it will add those 2 vectors. It'll add this and this together, element-wise, right? This plus this, and this plus this, and put that as the column 7 of this ratios. But not quite yet. We haven't computed the ratio yet, but we're in the middle of it. So it's cash plus short-term investments plus receivables. And receivables were column 18 here, which should be column 17. Here, yeah. So all of that in the numerator, put all that inside parentheses. And that'll be one vector. It'll be one column vector once you add those things together. And we want to divide that column vector, element-wise division, element by element. So dot and a division. Divide that by the current liabilities, which we already have up here. Semicolon to end the line of code. This computes the quick ratio. On to the next ratio, which we're going to put in column 8. We're going to do the debt to assets ratio. So debt is total, is long-term, not long-term, is total liabilities, column 15 here, which would be column 14. Total liabilities, element-wise division, divided by total assets, which are in column 7. They're in column 8 here, but they're in column 7 here. Because we lost one variable moving from here to here. We lost the date variable, right? The day. All right, and then debt to equity is the next one we're going to do. So I'm just going to copy and paste this. I know it'll be slightly different. Same numerator, debt, but equity, and then this will be changed to equity. So debt, long-term, or total liabilities in the numerator, and then denominator, we want not assets, but equity. And equity, total stockholders' equity is in column 20 over here, so it should be column 19. And then two more things, the gross profit ratio. I've just picked a subset of the ratios. There's other financial ratios. I just picked ones that I knew I could compute with the data that I have downloaded. Like I can't compute the accounts receivable turnover or the inventory turnover ratios, not with this data because I don't have any information about accounts receivable. I don't have any information about inventory. This right here is total receivables, total current receivables, which includes accounts receivable, but other receivables as well. This is an accounts receivable. So I can't compute those ratios. I'm only computing the ratios that I can compute. So we have the gross profit ratio, which is, in the numerator we have what? Net sales revenue minus cost of goods sold. Net sales revenue is in column 19 of this, so it's in column 18. And then we want to subtract that from that column, element-wise. When we do addition or subtraction, though, we don't have to do the dot like this. Usually with division or multiplication, if you want to do element-wise division and multiplication, you know, when we're using vectors, you have to use this and then either that or that. But with addition and subtraction, you can do element-wise without doing that. So just minus, so we got net sales revenue minus cost of goods sold. Cost of goods sold was in column 10 here, so it should be in column 9. All rows, column 9. That's in the numerator. And then in the denominator, we're going to divide by our net sales revenue. But we got to divide element-wise. This is our net sales revenue. Semicolon. This computes the gross profit ratio. And then finally, I want to compute the book value per share. in column 11 of our ratios matrix. The book value per share is, I'm trying to remember, total stockholders' equity minus preferred stock, so we just have our common stock, divided by the number of common shares outstanding as of the end of the year. But you have to adjust those common shares outstanding. No, that's not. In the book value per share formula, sorry, I'm wrong. It's total stockholders' equity minus preferred stock divided by the number of outstanding shares of common stock at the end of the year. But you have to adjust. Yeah, so what I said originally was correct. You do have to adjust those common shares for any stock splits or dividends given in the past. So we have to use that cumulative adjustment factor. All right, so we're going to have total stockholders' equity, which is in column 19, minus the preferred stock, which is in column 17, which would be column 16, because we lost our day variable earlier. Whoops. We want to take that and we want to element-wise divide that by the number of shares outstanding at the end of the year, which was in column 11 here, so it should be in column 10 over here. But we have to adjust this using column 5 here, which is the adjustment factor. So the number of adjusted shares outstanding after any stock splits or dividends that happened in the past is this times this. So we want to divide by, in parentheses, the adjusted common shares, which is column 5, all rows, element-wise, multiplied by column column 10. And this parentheses ends. Sometimes it's difficult to know which left parentheses is this right parentheses ending. And if you just click right here, you see it underlines this right parentheses and it underlines over here this left one, so you know exactly. Makes it easier for you to follow your code. And then put a semicolon. So I've computed the book value per share. If I did not do this multiplication right here and I just divided it by, if I would have left this off right here and just divided it by the number of common shares outstanding, that's unadjusted, right, for stock splits or dividends. So in any of those quarters where there was a stock dividend or split previous to that quarter, this would be incorrect. So we got to keep that back in there. And I believe those are all the ratios I can compute that don't involve multiple quarters. There's 3 other things I want to compute: return on assets, return on equity, and earnings per share. But those involve, you got to have 2 quarters of data, because the denominators of those ratios are an average. So I can't compute those ratios yet. Let's run this though and see what we have. So it finished already. And let's look at our first little matrix, first little firm. Oh, right here. And here it is. Column 6 is the current ratio. So this number should be the current assets for this firm in this quarter and this year divided by the current liabilities for this firm in this quarter and this year. So column 6 is column of the ratios is column 6 of the firm's matrix divided by column 13. And if we look here, column 7 was current assets of the initial data, so column 6 of the firm's matrix should be current assets. That's right, divided by current liabilities. So current liabilities here is column 14, but in the other one it's column 13. So we did this correctly. if we look at our ratios, matrix, that's the current ratio. This is the quick ratio. This is the debt to assets ratio, debt to equity, gross profit ratio, and book value per share. For that particular firm across the sample time period. Notice in this, in our exercise today, we're dealing with panel data. I meant to mention this at the beginning. Panel data is where you have multiple firms and multiple years per firm. And so that's what we're dealing with. Or another way to define panel data is we have a cross-section of firms for each year. In other words, we have many years, and for each year we have many firms. That's panel data. I did not have to put space in between here. I just did that sometimes for you to follow it, but I want to be consistent. So we computed those ratios. We've done this for each firm. If I looked at the second firms, and there's its ratios. Now we weren't able to compute the ratios for this particular firm as much. There was only certain quarters where we could actually have the available information to compute the ratio. Looks like only in the fourth quarter, for whatever reason. The first through third quarters are missing for this particular firm across these fiscal years. Therefore, the ratio information is missing. And now we want to compute the ratios which involve multiple quarters, e.g., the average of something in the denominator, for example. Usually that's how you get a ratio involving multiple quarters, is if it has an average in the denominator. All right. Now we can't just do it so quickly by taking the whole column, and dividing it. We have to check, We're going to do it. I don't know how to describe this, but we're going to do this sequentially. Let me show you what I mean. So if I just want to let little a equal firms 1, 1. That way I don't have to keep running this code and it keeps being put as answer, but the answer keeps getting redefined every time I run a different line of code. But now we have this thing. This is always the first firm. So in this first firm, now I want to compute let's say the return on assets, which is net income divided by total assets value at the end of the quarter. So initial data, net income should be, this is in column 16, so over here it should be in column 15. Total assets should be in column 7. Here it's in column 8. So net income divided by the average of total assets. This is the assets value at the end of fiscal quarter 3, fiscal year 2013 for this firm. And this is the net income right here for fiscal quarter 3. So I can't compute the return on assets for fiscal quarter 3 for this firm because I don't have the value of total assets in fiscal quarter 2 at the end of fiscal quarter 2 in 2013. I can't compute the average, right? The return on assets is the net income divided by the mean, the average total assets. So the first fiscal year quarter I could compute the return on assets for this firm is the fourth fiscal quarter 4, fiscal year 2013. And so for that fiscal year quarter combination, the return on assets would be this number divided by the average of these two numbers right here. So that's what I want to write a line of code that does this. Write some lines of code. For fiscal quarter 1, 2014, what's the return on assets? It's going to be fiscal quarter 1, 2014's net income divided by the average total assets between fiscal quarter 4, 2013 and fiscal quarter 1, 2014. But I don't want to be computing the average of these numbers if these two fiscal quarters differ by more than one, right? If these aren't subsequent fiscal quarters or consecutive fiscal quarters, then I don't want to compute the average of these two numbers. That's meaningless. So I have to write something in my code to make sure that I'm computing a meaningful average. In other words, think about it this way. Let's say for fiscal quarter 4, fiscal year 2013 for this firm, what condition has to be satisfied for me to be able to compute return on assets? Well, these 2 years have to be the same. And this must be one bigger than this, right? If we move down here to this case, then this year has to be one bigger than this, and the difference between these two numbers has to be -3. 1 minus 4 is -3. So if either of those conditions, if both of those conditions, so either the 2 years have to be the same, and this fiscal quarter has to be one bigger than this fiscal quarter, or if the 2 years are different, then they can only be different by 1, and this fiscal quarter has to be 3 less than this fiscal quarter, or this fiscal quarter minus this fiscal quarter has to be a -3. If neither of those conditions is satisfied, then I cannot compute the return on assets for that particular firm year fiscal quarter. Those are the two conditions that have to be satisfied. And this is what I'm talking about in Matlab. You really get to see the data, so you know exactly you're doing things correctly. In SAS, you would never have to do those mental gymnastics. You would have to think. SAS doesn't really require you to think much. Matlab requires you to think, but it's so rewarding once you get the hang of it. You understand the data intimately. It just makes everything so much easier. There's a little bit of startup cost at first, but man, the reward is amazing. You just become so good at data analysis. So you can just visualize everything. And almost like anything else in life, short-term pain for long-term gain. But if you want no pain in the short term, you don't really get much benefit in the long term. So many people can code in SAS, but they have no idea what they're doing. And they're making mistakes. They don't even realize it. You can't depend on the software program. You got to make it do what you want it to do. And so MATLAB's perfect for that. So we need to write a for loop. For I equals 1 to 1. So how many ever firms we have, which is the size of U in the rows direction. And I'm going to say for J, we're going to have nested for loops, a for within a for. For J, we're going to let J start incrementing at 2, increment by 1, and only go to whatever the size of this particular submatrix is in the rows direction. How many ever observations we have on that firm? So, again, the condition that has to be satisfied for any firm, any firm fiscal quarter, we can only compute, for a given firm fiscal quarter, we can only compute return on assets if one of two conditions has to be satisfied. Either these two fiscal years are the same, and this fiscal quarter minus this fiscal quarter is the number 1, or if that's not true, then the two fiscal years have to only differ by 1. This fiscal year minus this fiscal year has to be 1, and this fiscal quarter minus this fiscal quarter has to be -3. If neither of those conditions are satisfied, then we're not dealing with consecutive fiscal quarters. We're dealing with non-consecutive fiscal quarters, and the average is meaningless. So how do we write that? It's an if-then statement. So if the difference, so there's a diff function. Let me just show you how diff works. So diff, let's take diff of this first firm's matrix, which I just called A. Diff of A these two rows, column 2, or I'll just take the first 2 rows of column 2. What does that do? What it does is it subtracts, so the diff, here's how diff works in general. Let me just put a vector into diff, a vector, a column vector, 1, 2, 4, 5. What it does is it takes this minus this, so 2 minus 1 is 1, 4 minus 2 is 2, 5 minus 4 is 1. So it just computes the difference like that. So the diff between these two numbers has to equal 0, and the diff between these two numbers has to equal 1. Again, it's taking this minus this. Or the diff between these two numbers, you know, this minus this is equal to 1, and the diff between these two numbers, this minus this is equal to -3. That's the condition that has to be satisfied. Those are the two conditions. So if diff rows j minus 1 through j, column 2, so if that difference is 0, and ampersand means and the difference j minus 1 rows j minus 1 through j, column 3 is equal to 1. So if that holds, or if this other condition holds, the difference, here I can just copy and paste. The difference between fiscal years is 1, and the difference between fiscal quarters is -3. So it's either one of those conditions. So if this holds, which is an and statement by itself there, or if this holds, then let ratios row j, column, we were using column 11 up here for the book value per share, so we'll use column 12 for return on assets. Notice up here, though, we defined column 11, just all the rows immediately, just by this. But here we're defining column 12 row by row, because we have to check this condition right here, because computing return on assets involves multiple quarters. So then the ratios, row j, column 12 will be equal to the return on assets. So return on assets, row j, column 15, that's net income, divided by the mean of j minus 1 through j, column 7, which is assets. So this is net income, and this will be the mean of the assets across these two rows. And we're dividing one number by one number. So we don't need element-wise division, because it's one number divided by one number. Also, if that condition up there is satisfied, those conditions are satisfied, then we can also compute return on equity. We'll put that in column 13. And that return on equity is net income in the numerator minus preferred dividends divided by total stockholders' equity. So net income minus preferred dividends. And preferred dividends, over here we're in column 12, so they should be in column 11. It's this DVPQ. So that's in the numerator. Net income minus preferred dividends. And we're dividing that number by the total stockholders' equity. By the mean stockholders' equity. Last quarter to this quarter. The mean so J minus 1 through J. And then stockholders' equity is in column 19, if I recall. We don't have to have these two parentheses. We haven't violated any order of operations here. We do need these two parentheses though, because we got something minus something in the numerator. And if we want that all divided by this thing, then we need to put parentheses around it. Otherwise we'll get something that we don't want. And then finally, in column 14, we're going to have earnings per share. And earnings per share is the hardest one to do. We're going to have, in the numerator of earnings per share, it's the same numerator as in the book value, as in return on equity. Because it's the earnings per common share. So we need net income minus preferred dividends divide by, and now we want to divide by the average number of common shares outstanding. The average number of common shares outstanding. Common shares outstanding is in column 11 here, so it's really going to be in column 10. And the cumulative adjustment factor is in column 6, so it's really in column 5. So if we come over here, we want to take this number times this number and get a number, and then take this number times this number and get a number, and then take the average of those two numbers. That'll be the mean adjusted common shares outstanding. We have to multiply the shares outstanding by the adjustment factor. Obviously, it won't change things if the adjustment factor is 1, but if the adjustment factor is not 1, like it is on some of these rows, then it will change things. So it's the mean of this number times this number, get that one number, and then take the mean of that number and this number times this number. So the way we do it here, if we write it out, let's take the two numbers multiplied by each other first. So firms 1I, row J. So what I'm going to do is I'm just going to get these two numbers right here, and then element-wise multiply them by these two numbers, and that'll result in a 2-by-1 vector, and then just take the mean of that 2-by-1 vector. So element-wise multiply by, and then just take the mean of that 2-by-1 vector. And that should be the mean adjusted common shares outstanding as of the end of the year. So this should be earnings per share, basic earnings per share. All right. So we did our if. So if this condition holds, notice you don't put a semicolon at the end of the if. That's the only place here where you don't do that in Matlab, is at the end of the if statement. So if this condition holds, then do these three things. But what if that condition does not hold? We always have to have an else line. Else, if that condition does not hold, then let the ratios, that row, all the columns, equal NaN, which means we couldn't compute the ratio. So really, this if statement right here is basically making sure that we have consecutive quarters, and if that is the case, then we can compute these ratios, which involve averages in the denominator across the two consecutive quarters. But if that condition is violated, that means we don't have consecutive quarters and we cannot compute the ratio. So now we want to end our if statement. Then we want to end our for statement with the j. And then we want to end our for statement with the I. But before we do that, I want to type one other line of code. So what we've done is row j of this ratios matrix starting at 2 has been defined for columns 12, 13, and 14. But what about row 1 of the ratios matrix? It's just going to automatically give that row on these columns, 12, 13, and 14, just give that row the number 0 because I haven't defined what I want it to be. And we don't want the ratios to be 0 there. So I'm going to have to define them finally before we leave this part of the loop. So after the j has run its course, we've incremented through j, I'll have to go back and define row 1, columns 12 through 14 of each of these ratios, little matrices, nan. You can't, for the first row, you can't compute the ratios, right? Because you need the previous row and for the average for the denominator, and you don't have it. And now finally I end the first for loop. All right. And that should finish out our ratios matrix. So if we look at our first, I haven't run this yet, but if we look at our first, let me see, I'll see this. If we look at our first ratios matrix again. We have current ratio, quick ratio, and so forth defined. And then in column 12, we're going to have our return on assets. We go row by row, right, and compute it based on row by row in the corresponding firms matrix, if we have the information to compute it. And then 13 will be return on equity, and 14 will be earnings per share. Let me run this. Notice this takes a little bit longer because we have nested for loops. It's already done, but we have nested for loops. For each submatrix, 1i here, we have to go row by row, right? J goes all the way through that submatrix. And now if we look at ratios 1i now, for our ratios 1, 1, the first one now, we see these 3 rows are given nans because of this line of the code. And these other rows, this is the return on assets, this is the return on equity, and this is the earnings per share. And now, the final thing we do, let me see, I'll see this, is we want to combine firms into one double array again to form final data set. Whoops, I meant to put that up here, sorry, in our script file. Now what we want to do is we want to stack these ratios, the ratios data, back on top of each other. In other words, I want ratios 1, 1, and then ratios 1, 2, and then ratios 1, 3. I want all the data stacked again, back up in this format like this, like we originally had it, and we had all the data. Except now we are not going to have these variables here. We're going to have the ratios variables. And so to do that, that actually requires a little bit of thought. I'll just go through it, and you can study this code on your own to see how this works. I don't have the time to explain and go, I mean, I'd spend 10 hours in one video. going through the logic very carefully with you, but you have the code and you can go see how each of these lines is manipulating the data. So what we want to do is we want to find first the size of each of these ratios submatrices. So we can go how many of our firms we have, because that's how big the ratios cell array is in the columns direction, how many of our firms we have. Or I guess to be very careful, we can go ratios, the size of ratios in the columns direction, which is 19,363. And we're going to let Si of 1, this little column vector, each row of it is going to be the size of the corresponding ratios submatrix in the columns direction. So this gets size of each firm's array. In other words, how many observations we have for each firm. Oh, whoops. Ratio doesn't exist. I haven't defined that yet. It's ratios. Sorry. Size is not a function. It's size. Sorry. Sloppy. All right. So if we look at our S, the first firm had 40 observations, the second firm 28, the third 40, the fourth 40, and so forth. And that's important. Now we're going to let S equal, we're going to put a 0 at the top of the S column vector. So that makes it look like this. Just added a 0 right there and then put everything else underneath it. And then we want to get the row numbers for indexing. So in the second column of S, we want that to equal the sum of S rows 1 through I in the first column. This is going to help us define our final data matrix where we stack things back on top of each other. We have to know which rows to put the things. So in our matrix that we stack on top, rows 1 through 40 will be ratios 1, 1. Rows 41 through 68 will be ratios 1, 2. Rows 69 through 108 will be ratios 1, 3, and so forth. So now we run our for loop again. I goes from 1 increments, starts at 1, increments by 1, and goes up through the size of our S matrix in the rows direction. -1 though. We don't want to go all the way to the very length of S. We're going to call it final ratios data. And rows S, I column 2 plus 1. So when I equals 1, it's S1, 2, this number plus 1, so 1, through row S, through this number, right? So through S, I plus 1, column 2. We want those rows, all columns of our final ratios data to equal ratios 1I. So it's a stacking of all the individual firms' ratios data. We'll run that. That stacks the firms back on top of each other to form one big matrix, instead of each firm having its own little submatrix. We had to put each firm into its own little submatrix so that we could compute the ratios for each firm. But then after doing that, we put them all back together into the big matrix. So this little blurb of code here is used, I use this all the time, to take a set of double arrays and combine them back, stack them on top of each other. So if we look here at final ratios data, notice it has the same number of rows as our A originally had and as our initial data originally had. It has the same number of rows. And so here's firm 1004 and all of its ratios. Current ratio was column 6, column 7. I can't remember how I defined. Go back in the code here and look. Columns, this is why I type comments to myself. Column 6 was current ratio. Column 7 was quick ratio. Column 8 was debt to assets. Column 9 was debt to equity. Gross profit ratio. Column 10, book value per share. Column 11. Column 12 was, right here, was return on assets. 13 was return on equity. And 14 was earnings per share. So those are the ratios. For all the firms, now we have our panel data back together. So for all the firms, for all the fiscal years, for all the fiscal quarters, here are our ratios. Across all the panel data. Go all the way down to the bottom. Of course, there's a lot of missing observations where we couldn't compute the ratio. I just saw a negative inf there in one cell. Negative infinity right here. And that's in column 10. Let's go back. Column 10 was gross profit ratio. What's the denominator of gross profit? It's net sales revenue. The gross profit ratio, net sales revenue. So that must be inf right there because net sales revenue in that quarter was 0. And so it computed an infinite ratio. Something divided by 0 is infinity in Matlab. So what we could do is go back and change all the places in this matrix where it says negative inf and replace that with nan. That's basically not applicable. You can't. It doesn't happen very often. But it did happen some. So let me see if there's a quick way to teach you how to do that. There's a function in Matlab, isInf. And it's a logical. It produces a logical. And here's what the output will be. It'll just be a big matrix of zeros and ones. There's a 1 in any cell where there's a corresponding inf in the data. So I think all I have to do is do something like this. First of all, I want to make sure that we check and make sure. So this row 405976 column 10 is a negative inf. And after I do this code that I'm about to do, I want to make sure that this is replaced with nan. Make sure I did it correctly. 405976. I'm going to go ahead. Final ratios. Data. 405976 column 10 is negative inf. All right. But now I'm going to type some code here. I'm going to do final ratios data. Any place you see in that matrix, rows or column, any row column combination where you see, if you see a 1 there, I want to replace that with nan. Oh, replace that with nan. 1 equals means assign something equal to something, and 2 equals means it's actually equal to, if you know what I mean. So I didn't say that earlier, but that's why I had the 2 equals up here and not 1 equal. 1 equal here would be an error. You're saying if this thing is assigned to 0, it would say, assign it to 0. Are you wanting to assign it to 0 or not? See? But I had 2 equals up here because I'm saying if it's equal to 0, not assigned to. So here we're trying to assign all places in the final ratios data which are inf a nan. Let's run this. And then let's rerun this right here and see if final ratios data row 405976 column 10 is still inf. It should be nan now. And it's nan. And we can look and see right there it's nan. It's not inf anymore. So that's the final line to replace. So a zero denominator originally produced this. And then the final thing we want to do is take our double array and convert it finally back to a table array so we have variable names. Because we can't remember what these variables are. I mean, we can remember if we go back in our code, but we're going to forget. So this is GV key, this is SIC code, this is fiscal year, this is fiscal quarter, this is fiscal year end month, this is current ratio, and so forth. But let's go back and so now put back into table with variable names defined. I'm just going to call the table ratios. So financial ratios equal, and I'm going to use an array to table function. It converts a double array back to a table. What double array are we wanting to convert back to a table? This final ratios data double array. That's the first argument of this function. And the second argument, we have to choose variable names. What do we want to name the variables once we convert this back? The first variable, GV key. So the variable names have to be enclosed. This is the syntax in the squigglies. Second variable is SIC code. Third variable, fiscal year. Fourth variable, fiscal quarter. Fifth, fiscal year end month. And then what I'm going to do is put 3 dots here because my code is just going to go way. I'm just going to keep, because how many? There's 14 columns here. I gotta name I gotta give 14 variable names, and I've only given 1, 2, 3, 4, 5 thus far. I misspelled this. I've only given 5, so it's just my code's going to go way over here. So if you ever want to keep your code from going all the way over there, just put 3 little dots like this, and then you can hit enter. And you can go to the next line. I'm going to make it line up with the line above it. And those 3 dots, Matlab knows to read. It's as if those 3 dots weren't there and whatever's down below it is still attached right beside it. Sixth variable is current ratio, column 6. Column 7 is quick ratio, if I recall. Column 8 was the debt to assets, 9 was debt to equity, 10 was gross profit, 11 was book value per share. I'm going to put those 3 little dots again, come down here. Um, 12 was return on assets. 13 was return on equity. And 14 was earnings per share. End it with a semicolon. And that's it. Delete those other lines of the code. And then let's run this final line of code here. Or this final bit of code. I must have messed up. Oh, I messed right here. I put something in there, that character that shouldn't have been there. Oh, we have an error here because of this red right here. It's this should be like that, and then this shouldn't be there. This shouldn't be there. Oh, we didn't close the parentheses. There's a left parentheses here. And yeah. There should be a right parentheses there. And a right, or a right, whatchamacallit, I'm having a brain fart. Whatever you call this thing. Curly brace, right curly brace, and right parentheses. Now we can run this. And it should run just fine. And it does, and here's what our ratios table looks like. There we go. We have our column names, DB key, SIC code, fiscal year, quarter, year end month, current ratio, quick ratio, debt to assets, debt to equity, and so forth and so on. And now, anyway, I hopefully you enjoyed this video and you learned something, and I will see you on the next one.